Good afternoon, folks. I'm happy to be speaking here, and all the folks who are online, welcome to this talk. I'm going to talk about machine learning and IoTs today. And let's switch to the slides. If you have any questions, please type them in the chat box. I will not be able to see them, but once I'm done with the presentation, then I'll get to those questions. So I'm going to share the slides right now. Okay, so how do we use machine learning in the cloud on IoT data? So that is a topic of today's chat talk. And here is the agenda, what I'm going to use. So first I'm going to describe how a typical IoT system will look like. And then I will talk a little bit about the characteristics of IoT data, how it is different from traditional data that is used in machine learning. And because it is different, the machine learning techniques that are used for the IoT data are slightly different. And we are going to talk a little bit about that. Then I will talk about the IoT Devkit that Intel puts out and show how this IoT Devkit can be used for collecting data about the environment and about practically whatever that you can think of in the world today. And then most importantly, towards the end, what I will do is to show a complete end-to-end IoT solution that can be put together with the Intel IoT Devkit, and also pulling together a bunch of components that are available off the shelf out there in the market today. So those are the four sweet topics that I'm going to talk about today. Here is a typical IoT system that we are going to be looking at. Now this is showing a fairly complicated picture, but if you look at it from 10,000 feet, it is fairly simple. So there are three basic components in this system. One is the one on the left, which is the edge devices. And these are at the edge devices, we have typically the sensors, which are collecting data about the whole environment and about the system in which they are trying to monitor. And then we also have some actuators which are trying to control those systems. For example, if you have a motor that is trying to do something based on the needs and based on whatever it is supposed to be doing functionally, it could be controlled. Its speed can be increased or its speed can be decreased based on the environment. So that is the edge side of things. Now in the middle is the network. And this is the place where the data that is collected from the edge is aggregated and then transmitted into the cloud. And of course on the right is the third part of the IoT system, which is the cloud. And this cloud is aggregating the data that the edge is collecting, and it is analyzing them and then applying various analytical techniques on them, and then identifying what are the different insights that it can gain out of the data that is being collected. And then based on the insights that it gets, it is going to have a feedback loop where it can control the edge devices so that they can perform better or they can perform more efficiently. So that is the overall IoT system in a very abstract sense. Now here is a real IoT system that is deployed actually right in my house. And this IoT system is a solar electricity generation system. And at the edge, what we have are something called the microinverters, which are shown in this little box. Now, each of these microinverters are connected to each of the solar panels. And currently I have about 22 solar panels and then 22 solar inverters. Okay, so here is the real IoT system. And this IoT system is having solar panels, 22 solar panels, each of them having a microinverter. And the microinverter is the edge device, which is generating information about how much solar energy is being generated by the panel and the inverter. And then that information is fed into the power mains, which is this picture here. And these power mains are the ones which are collecting that information and then sending them off into two different systems. One of them is the gateway from the company which makes these power inverters called the NY gateway. And then also it is sent into the Austin Energy, which is the energy company that supplies power to me. And this information is aggregated by both of these systems. And then from the NY gateway, it is connected into the network, into the internet through my modem router and the modem at home. And then it is sent into the servers of the Enphase. Enphase is the company which makes these inverters. And then they provide access to all of the data so that people can look at how much electricity is being generated and whether their system is working efficiently or not. And if by chance these power inverters fail, then a notification will be generated and the company gets a notification, and then they can immediately rectify that. Because if the panels are not working efficiently, then, or if the inverter is not good, then it is a loss in revenue for myself. And therefore, I want all of these gateways and inverters to be working efficiently, and they're up all the time. And then the same thing is true for the Austin Energy, which is trying to monitor how much energy I am generating, because they're paying me money for generating this electricity. And of course, the advantage of the Austin Energy or the energy company here is the fact that they do not have to invest in the peak energy consumption. In summer, when people turn on their air conditioning units, that is the peak energy consumption. And if people, or if the energy company has to satisfy the peak energy consumption, then they have to invest heavily in the infrastructure. Now, by distributing the cost of the infrastructure to the homeowners, they're able to reduce their capital expenditure. And therefore, it is an advantage for them also to ensure that these systems work most efficiently. So that is a real IoT system, and it is very important that these systems work very efficiently. And the data that is being generated will be used and also will be adequately monitored so that the system will be functioning at its peak efficiency. So that is a typical IoT system and a real life example of that. Now, what we're going to talk about is what are the characteristics of this IoT data and what kind of machine learning techniques that we want to use on that IoT data and what kind of insights we want to get from that IoT data. So here is the example of that. So the first thing about the IoT data is that it is a streaming time series data. Now, what does that mean? It means that the data that is being generated is one of the key components is time. Now, if you take the example of the previous solar system, the data that is being generated is the instantaneous power that is generated at any point in time. And it is sampled every few seconds, and you know that a certain amount of power is being generated at every point in time. So that is streaming time series data. Now, contrast that with the non-time series data, which is people buying some items on the web. That is not really time series data, although there is a time component to it, but it is not really a time series data. It is more of event data. And the events are more of things like purchasing some item. So the time series data is very critical in the sense that it is generated at fixed time intervals, and also the inference of the results from this time series data results in some real-time actuation. So unlike the traditional machine learning data that is generated by other systems, the IoT time series data typically involves taking some real-time action based on the insights that you get. An example again is if the microinverter in a solar system is not working, then you would want a call to be generated so that somebody can go and then fix that. Or if the system is not working at its peak efficiency, then we need some notification saying that one of the inverters is not working or one of the panels is broken. The next one is that the data is highly correlated. What this means is that the data that is generated at time n-1 is kind of related to the data that is generated at time n. Again, going back to the example before, if you're generating X amount of kilowatt hours at time n-1, then typically you expect that you're generating some X minus or X plus some value of kilowatt hours of electricity in the next time interval. So the data is highly correlated. Now contrast that with other kinds of data where the fact that somebody bought a item does not mean that some other place they're going to buy the same item. There is not really any correlation between them. So the data is highly correlated in the case of IoT because it is time series data and there is a strong relationship between what happens in the near time interval to what happens in the next time interval. Now, the other thing is that there is a lack of training data for whatever insights that we want to capture, or the data is highly imbalanced in the sense that you will have data where things are working all fine. For instance, the solar panels are generating electricity, but suddenly once in maybe a year or once in maybe half a year, a microinverter might go bad and then suddenly it stops working. So that is highly imbalanced data because in the sense that you have lots and lots of good data where the system is working very efficiently, but occasionally you will see a data which is where the system is not working efficiently. So that is a very imbalanced data. So it creates very big challenges in terms of trying to detect the anomalies or trying to gain insights into what the data is telling because of this imbalance. Because traditional machine learning techniques cannot be used for gaining insights in here, and special techniques have to be developed for this. So those are the four key factors that differentiate the IoT data from rest of the traditional data that is used in other fields. What are the machine learning techniques that are being used in the case of the thing? So one is the rule-based systems. So in the case of rule-based systems, what we can do is based on some heuristics, we can determine that a certain value is bad, and therefore we can flag that. So these are simple things like if the temperature inside a room is 100 degrees centigrade, then either the room is on fire or the air conditioning unit has broken down or it is a sauna. So simple rule-based systems. And what I'm going to show later here is a simple rule-based system which detects that that a building management system is not performing very well. So rule-based systems have been in existence forever, and then humans use heuristics and then come up with these rules pretty easily. Now, the second one that people commonly use for IoT data is what is called the one-class support vector machines, or OCSVM. And what these one-class support vector machines do is try to detect anomalies in lots of normal data where there are not many cases of anomalies. So in the traditional machine learning parlance, it is called supervised machine learning. And what it does, it recognizes the patterns. So essentially what it does is it infers the properties of one class of data and then identifies the data points which do not have those properties. So examples again are when you have a large number of good credit card transactions and then very few bad credit card ones, bad credit card transactions, then you can determine the properties of what the large number of good credit card transactions are and see if those properties are violated in a transaction to label them as bad credit card transaction. So that is how a one-class support vector machine works. The next one is PEWMA, probabilistic exponentially weighted moving average. And this is used for, again, streaming data analysis. And what this does is it detects abrupt changes in transient data or a abrupt shift in the underlying distribution of the data. So for instance, the temperature is 10 degrees centigrade during winter, and during summer, it suddenly becomes 30 degrees centigrade. So that kind of changes the PEWMA can detect very nicely. And then the other one is Markov models. These are used to predict sequences of events based on historical data. And whatever patterns that are present in the historical data, it can learn those patterns and then predict what the future is going to be. And again, this is based on, these are used for predicting the failures inside the machinery or failures inside any other system. So these are the machine learning techniques, and there are a few other machine learning techniques that are out there, but these are the primary ones that are used in the field today. So those are the characteristics of the IoT data and the machine learning techniques. So the Intel IoT Devkit overview, so I'm going to go briefly over this. So there are lots of Intel IoT platforms in the market today. We have things like single board computers with exposed IOs. So these examples of these are Galileo or X1000 or Edison's. And then we have microcontrollers, D1000, D2000, C1000, which are used for building variety of different edge devices. And then Arduino 101 is again an MCU class of machine. And then we also have the gateways or the PC class machines, which are used for aggregating the data that is collected by various IoT devices, and then use them for detecting the information. So these are the platforms that are in the market today. And what people can do is to use them to build and collect data very easily. Now, that is the hardware that is available. And then the IoT Devkit is the software stack that runs on this hardware. And this contains at the bottom the operating system images. We support a variety of different kinds of images, the Wind River Linux, Pulsar Linux, which is a small footprint Linux. And then Zephyr is a real-time operating system. The standard Ubuntu is supported, and then Windows IoT is also supported on some of the platforms that we have in the market today. Now, having the operating system is not enough because you want to be able to connect various sensors. So there is a variety of middleware that is connected to this. And this middleware is used primarily for collecting the information from the sensors. And then, of course, once you have the middleware, you want to write some programs. And we have different kinds of tools. We support Arduinos, we support XDK, which is a JavaScript-based tooling platform for developing software for controlling these devices. And then the Intel System Studio for C and C++ languages, it is supported. And we also support Node, Python, Node-RED, and so on. And of course, at the cloud, we connect to a variety of different cloud providers that are out there in the market today, Microsoft Azure or IBM Bluemix. So all of these things are supported. The goals of the IoT Devkit are provide good out-of-box experience. Once a customer gets the box, they can start programming them and collecting data and start getting insights very quickly in less than an hour. A large number of sensors and peripherals are supported here. So more than 300 different sensors that are out in the market today are supported with Intel platforms. A uniform development environment is supported. The exact same set of tools are used for programming in the cloud and also programming at the edge. The Eclipse-based tools or Node-RED or JavaScript, so the exact same environments are supported. A very robust developer ecosystem is present around the Intel platforms. And then, of course, variety of different cloud providers are supported here. Now, depending upon the vertical in which people are interested, these different kinds of systems are, kits are available. If one is interested in environmental sensing and environmental IoT, there are kits that are supported, which contains a bunch of environmental sensors. And if somebody is interested in robotics, there are robotic kits that are available. And all of them support the Intel IoT Devkit, which will enable people to build solutions for whatever problem that they're trying to solve. And the link here shows the places where different kinds of of kits that are available in the market today and where they can buy them. Now, this sensors and the libraries. So the MRA is a library that is supported on these platforms, which will enable people to attach different kinds of sensors and then collect data from those sensors. And irrespective of what kind of board is used underneath, the sensor will work if they're using the MRA or the UPM APIs. So it will make the application hardware agnostic in terms of ensuring that people can move from one hardware to another hardware with little or minimal changes to their software. The developer kit contains the IDEs which are used for programming these systems. The Intel XDK is primarily a JavaScript, and Node.js applications are developed using this XDK, and one can create really powerful applications using that. It contains the whole debugging environment, very rich environment. And the Intel System Studio is a Eclipse-based tooling suite which contains support for C, C++, and Java. And all the platforms that I showed before can be supported with these tools. There is a rich developer ecosystem that is out there. There are lots of hackathons that happen based on Intel hardware, and people can participate in that and then develop cool systems. And a lot of that information is open sourced, and then most of those designs are present on hackster.io or a lot of these code sharing sites. Most of the code that is developed and all of the hackathons is available on GitHub. Again, lots of cloud services are available: Amazon Web Services, Microsoft Azure, or IBM Bluemix, GE Predix, or AT&T. All of these systems are available here. A complete end-to-end IoT solution is the next topic, the last one here. And the question here is to develop a setup where the temperature sensor data is plotted in the cloud, and when the temperature goes above a certain value, we want to send out an email. So that is a very simple solution that we would want to build. And the way in which we are going to build that is by as follows. So as I said before at the beginning of this talk, it contains the typical IoT system contains three components: the edge, the gateway, and the cloud. So for the edge, we are going to use a temperature sensor. For the gateway, we are going to use a Edison, which is a Intel platform. And then for the cloud, we are going to use the AT&T cloud. And there are two things in the AT&T cloud. One is called the M2X, which is a time series data store. And then we are going to also use Flow, which is a Node-RED-based system, which can get the data, store it, send it off into M2X, and then do some analytics there. So that is what we're going to do. And here what we're going to do is we're going to connect the temperature sensor physically to the Edison. Now, on Edison, we are going to run a Node-RED flow. And the Node-RED flow so this is essentially the entire program that is running on Edison. So there is a node called read temperature, which essentially says that it is connected to the analog port A0 of the Edison. And then it reads the analog port every 1000 milliseconds, that is one second, and then records the temperature. And then once it records the raw value, it is going to convert that into Fahrenheit. And the way in which it is going to convert that into Fahrenheit is by applying a formula which is based off of the sensor that is connected to that. And that formula is shown in this board, that is the JavaScript code that is present there. And then once that is converted into Fahrenheit, it is sent off into the cloud. And the cloud data is shown here. The address of the cloud is runeast@AT&T.io. So I already have an account in the AT&T cloud. And then it is sent off as a UDP message. One can send it off as MQTT message, or one can send it off as any other kind of message. In this case, I just chose it to be a UDP message. And then I send it off on port number 64914, which is shown here. Again, pretty simple here. And also, just for grins, what I do is I print the value that I get out of this node convert or the temperature. So that the screen that is connected to the Edison will have a rolling temperature that is printed on the screen. Now we need to set up the cloud service. So we need to open an account on developer.att.com. This will create accounts at the time series database service called M2X, and also a cloud service called Flow, which is the AT&T's cloud service. And then the flows that we create on AT&T are also Node-RED visual language. So essentially, we use the Node-RED both on the edge and also in the cloud. So that is what I was talking about, the similar programming environments available at the edge and the cloud. And they also need to set up the M2X time series database so that the Edison device is present inside the M2X so that it can stream its data into the M2X to a stream called temperature. And then once this setup is done, there are two keys that are given, and we need to make a note of those two keys so that we can attach them at a later point. So now we go into the AT&T's node flow, and then we create again a flow inside AT&T. And what we do is first we listen to the data, the UDP datagram that is being sent out by Edison. And once we get a datagram, we simply print for debug purposes. And then what we do is to send this off into the time series database. So this M2X message prep is a node which is taking the data that is received from this UDP, and then it is going to create a message that can be stored into the M2X time series database. And then once that is set up, we store the data, and then the keys that were, you need authentication, and the keys that were created before have to be plugged into this code so that the data can be stored inside the time series database. And then once the message has been prepared, we can simply send a message to the M2X to store that data. And these two keys are the ones that are given to us when we created the M2X service before in the previous slide. Now the program is done. So now what we have to do is to deploy it. So when you have a button in the AT&T service called deploy, and once you click that button, what happens is that there is a server that is spun up inside the cloud, and it starts executing this flow. And what this flow does is to simply listen to a port or a message, a UDP data message that is being sent to it with the appropriate authentication from the Edison. And it will, once it gets that, it is going to store that and then do whatever that we told it to do in the previous slide. And the way in which you programmed Edison is to get this data here, that the address of the IP address of the server that is inside the AT&T cloud, which is shown here, and the port number on which it is listening. So these are the two things that have to be programmed on Edison so that Edison can send the data out. And of course, the authentication has to be appropriately present there so that it can talk to the AT&T service that is deployed inside the cloud. Now, once this is set up, now we can go into M2X, and then the real-time data that M2X is getting from Edison is now plotted, and you can visualize this data based on the M2X that AT&T is providing as real-time. Now, it is great in terms of the data that is coming out, but there is another part, which is we need to send a notification when the temperature goes above a certain limit. So that part is programmed here. So inside M2X, we are going to add a trigger which says that if the temperature ever goes above 40 degrees, then we need to send a message back to Flow saying that the temperature data, the data that we received crossed a certain threshold. And that threshold, that is a post message that is being created here, and we just set that trigger. And that the callback URL is the one that is present here. So this is the one which sends a post message to the flow. And inside the flow, we need to change that so that we process this callback from the M2X service also. And the way we do that is, in addition to listening to the data that is being sent from Edison, we also add another HTTP in message. So it is also listening to a post message that somebody else is sending. And we say that if we receive that post message, we simply send an email using the Google mail service by using the send mail node of Node-RED, and then setting up our password and the user ID, and then using the Google mail server to send off that email to somebody who wants to get that notification. So again, what we have done here is to simply take off-the-shelf components, Google mail server, AT&T's cloud service, and then the edge devices that Intel and the gateway devices that Intel has supplied, and then create a complete end-to-end solution where we monitor the temperature inside wherever that temperature sensor is present, inside a room, inside a building, or inside a box, and then send off the data into the cloud service, and then send a notification through email to this. So in summary, we can collect the data, we can send a message into the cloud and store that data, and then apply, in this case, a simple rule-based machine learning to figure out whether that data is telling us something or not. We can also deploy other kinds of machine learning techniques, the SVM or the PEWMA also in a very similar manner. So that's it in terms of the presentation. There is a question there. So there is a temperature sensor that comes with the Edison kit, in the environmental kit that we supply, and we used that temperature sensor in this application. And again, the sensors are the MRA and UPM sensors are fairly easily available in the market as kits and also as individual sensors. And if you go to Intel's website, you can find all the places where these sensors can be purchased, and they're fairly inexpensive. These are not industrial class sensors. For experimentation, you can use normal El Cheapo sensors, but if you want to deploy industrial class applications, then you can go and then get more hardened and more accurate industrial class sensors, and obviously they cost more. But for experimentation purposes, you can use normal sensors. And the libraries that Intel supplies support both the cheap sensors as well as the industrial sensors. Thank you.